Okay, for today's lecture, and as I said, we were looking at the addition of waves, and I told you that a phasor, by choosing the complex number e to the I omega t, and taking the real part that represents, say, wave 1, wave 2 would be similar, and then addition of these two vectors can be done either by typical complex number addition algebraically like this, and that will give you the same answer as doing, say, a vector addition. Like, so if I try to calculate the magnitude of that vector, I would just use the parallelogram law, or I can complete I can take this triangle and use the cosine rule, whichever way you want to think about it. I can find the magnitude of that vector, then I can calculate the angle as well. But here it becomes much more simple algebraically to just like add up the x, that is the real parts and the imaginary parts, and that immediately gives you the full vector, both the real and imaginary parts. And from that, I can convert it back to polar form. So if anybody is unfamiliar with how to go from the x plus iy form to the polar form, let me know. I can go over that once if you're not sure. So that is the, in terms of like complex numbers, we're just using those ideas again. And this complex number here, if I take the real part of this, again, remember, always we take the real part to find the actual resulting wave, will match up with the wave that we found way back in lecture, in week 2, when we calculated the sum of these two waves by just using cosine trigonometric identities. Okay. All right, and as I show here, there's another way to think about this. Using, instead of taking the real and the imaginary parts and adding them up separately, I can also write it in polar form. And so this is the polar form of the waves, psi1 and psi2, which is z1 and z2 are represented by this polar form, a to the I omega t, a to the I omega t times e to the I pi over 3. And now when I add them up, it becomes very explicit. There's this e to the I omega t, which is outside, sort of it's common to both of them. And then the part that affects the amplitude and the phase of this wave is 1 plus e to the I pi. And so to calculate, for example, the magnitude of this complex number, I would take itself and multiply it by its complex conjugate. Okay, so this is the complex conjugate. You can also, so from this you can calculate the complex conjugate, which to find here, the only part, the e to the I omega t, its complex conjugate is e to the minus I omega t. So that cancels out or gives you 1. And then you get 1 plus e to the I pi over 3 and 1 plus e to the minus I pi. So there'll be 4 terms there. There'll be 1 times 1, then e to the I pi over 3 times e to the minus I pi over 3, that'll give me 1. So that's 1 plus 1 here. And then there'll be a combination e to the I pi over 3 plus e to the minus I pi over 3. And that, by the earlier identities, is just 2 cosine pi over 3. So all of this added up together gives me the overall magnitude. That is this length of this phasor over here. And again, by calculating the real part of this complex number over here, you'll see it's identical to that earlier expression I wrote on the previous slide. I'll leave that for you to do as a small little check. It's fairly straightforward. Just take the real part of this. So, okay, but now I want to tell you about a way in which so far phasors have looked just like vectors, but there's one way in which phasors are not vectors. Okay, because you might think, why do I have a separate thing, this phasors? I just think of them as vectors. And in fact, there is a big difference between that and the way in which we're going to multiply phasors. And specifically, we can always multiply complex numbers. But what I'm trying to tell you is that a phasor, which remember is I have to take the real part of it to find the actual wave. The wave is always the real part of the complex number. Well, in that case, I can't multiply two phasors together to get the multiplication of two waves. So if I want to multiply two waves together, I can't do that by just multiplying the phasors, that is the complex numbers together. And that can be made immediately obvious by looking at psi1, which is a cosine omega t, psi2, which is a cosine omega t plus pi over 3. If I were to multiply z, that is the phasor z1 and the phasor z2, that's z1 star z2 using complex multiplication, I would simply get a squared e to the I 2 omega t plus pi over 3. And if I took the real part of that, I would get cosine 2 omega t plus pi over 3. Okay? But if I had taken just the original waves, psi 1 and psi 2, and multiplied them together, okay, that will give me cos omega t plus pi over 3. And by using the standard trigonometric identities, I get cosine 2 omega t plus pi over 3, which is good. That's exactly the real part of this guy over here. But then I get an extra term. So the real parts, if I multiply the real parts of psi, that is exactly the waves, the physical waves themselves, I get an extra term here, which is not in the complex multiplication. So we cannot just say that psi is equal to the real part of Z1 times Z2. So we can't just multiply the phasors and take the real part. That will not give you the right answer. Okay, so we have to be careful when we're doing multiplication of two waves. When we want to calculate the product of two waves, we first take the real part of the phasor and the real part of the other phasor, and then multiply them together. And at that point, you just have to take standard trigonometric identities or do other manipulations to get the answer in that case for multiplication. Okay. So just to summarize the phasor rule. So once you express a wave as a phasor, a complex function, and you want to perform operations with that function, then you can only recover the right answer, the real part, if all of these operations, as we call them, are restricted to this possibility, which is addition, subtraction, multiplication, or division by a real quantity. So as long as I restrict myself to that behavior where I'm only adding or subtracting or multiplying or dividing by a real number or a real function, and also I can differentiate or integrate with respect to a real function, get that a real variable. That's also allowed. As long as I do that, then all the phasor manipulation at the end, if I take the real part, I'll get the same answer as if I had done that with just the cosine or sine functions, the physical wave itself. Okay. And and of course, adding and subtracting two waves is allowed, and so is, but to find, say, the magnitude, we have to use the method of multiplying by its own complex conjugate. Because again, magnitude is like squaring the phasor, and as I just told you, multiplying two phasors doesn't give you the right answer. But magnitude is just phasor time its complex conjugate, so that's okay. I'll show you that in this slide over here. This is the special case. So I have two waves, I'm adding them together, as we've just seen, that's okay. Okay, but to find the magnitude, I don't want to just square it automatically. Because squaring is again Z1 plus Z2 times Z1 plus Z2 will not give me the right answer. But multiplying by its complex conjugate gives me the right answer. Because that's just the magnitude squared. Okay. And so the magnitude squared can always be found by taking Z1 squared plus Z2 squared plus, and this final term over here, which I've just written down, is just 2 times the real part. Now, not of Z1 times Z2, but Z1 times Z2 star. Okay, this is an important little term, which you can verify for yourself just by multiplying out all the terms in this expression, and then verifying for yourself that 2 times the real part of this complex number gives me those remaining 2 terms in this expression. Over. Again, I'm going over the math fairly quickly. If you have any questions, please stop me. So I'm now going to show you that this can be used to find the phasor representation of the pointing vector. Okay. So recall that we have a phasor representation for a harmonic wave, which is any regular wave. So the wave, the real part of it is cos kz minus omega t minus some phase phi, and I can write its phasor as a e to the I omega kz minus omega t, which is just a cosine plus I a sine kz minus omega t. And so if I now write it as just the phasor part, the complex amplitude, I would write e to the I kz minus omega t minus k phi minus phi. I've taken out the time dependence for a second, and so just the amplitude part would be a e to the I kz minus phi times e to the I omega t. Okay, a minus I omega t. So again, the same problem with the pointing vector. You may remember the pointing vector is the square of the phase of the harmonic wave. It's e squared. It goes as e squared. But because the pointing vector, for example, is obtained originally, if you look at the original definition, it's e cross b, which we showed was equal to e squared. Okay, proportional to e squared. So we can't directly take that product, or we can't directly take the product of E times B, or take the square of E, again, because we are forced to not do that by the phasor rules. But we can show, again, that we can obtain the intensity, the time average Poynting vector, from the phasor as follows. So I'm going to show you, here is just the two fields themselves at the same frequency. We're assuming the frequency is the same, because it is the same for that particular wave. And we're just considering the time average superposition of those two waves. Okay, so that is, I take two waves. One is E1 cosine kz minus omega t. The other is E2 cosine kz minus omega t minus phi. Okay, and then the time averaged Poynting vector, remember, is just the square. And then the time average is 0 to t, or t to t plus t, doesn't matter. And then there's the c epsilon naught. I think there's a factor of half missing here. Sorry, on this side, the factor is here, over here. Sorry about that. I left it out of the first expression here. So if I take the square of this quantity and calculate what happens over here, I'll get this. Okay, I'm not going through all the steps. You can verify it yourself. Now, if I consider the corresponding phasor for this, this is E10 e to the I kz minus omega t. This is E20 e to the I kz minus omega t times e to the minus I phi. Okay, so that since e to the I kz minus omega t is common to both of those values, I can just take E10 and E20 e to the minus I phi, and then I'll just form this magnitude squared. Okay, the magnitude squared, well, that is just this quantity times its complex conjugate, which again, by writing it out, is E1 squared plus E2 squared plus E10 E20 times the real part of e to the minus I phi. Okay, and that gives me cosine phi again. So the two are identical, even though I said that normally we can't take the square. This, as I said, I've skipped a lot of steps here, because basically I had to take each of these waves, square them, and take the time average of them. We have done something like this before, so I'm skipping some of those steps over here. Okay, but you can see now that it is indeed okay, as long as we take the magnitude squared of the phasor, that the time averaged intensity is going to be the same as simply taking the time average, taking the norm of the phasor squared. Okay, so as long as we do that, we are okay with squaring to find the intensity. So squaring the phasor to find the intensity, instead of just squaring it, we won't square it, we'll take the norm of the phasor squared. Okay, that's the important thing to remember whenever I talk about any further phasor diagrams, as we'll be doing in some of the later slides. Whenever I'm finding the phasor, at the end, when I want to find the intensity, I'm always interested only in the magnitude squared of that phasor. We'll always be considering the magnitude squared. And this is the proof that that is proportional, or is identical as long as I multiply by c epsilon naught over 2 to the time average intensity of the wave. Okay. All right. And this is, of course, I've done it for two waves. You can prove it for arbitrary number of waves by induction, or arbitrary phasor. So the final result, which is all you have to remember, even if you didn't follow all the math, is that the time average intensity is c epsilon naught over 2 times the magnitude of the phasor squared. Or since we don't usually care even about the constants, we'll just say as long as the phasor squared, the magnitude of the phasor squared is, say, increasing, then the intensity is increasing, or it's at a maximum when the phasor magnitude is at a maximum, or it's a minimum when the phasor magnitude is at a minimum. That's when the intensity will also be maximum or minimum. Okay. All right, that was just the math prelude. And so now we're going to go back to the Young's double slit and talk about the conditions for interference. This is just a reminder from the last class. When we discussed the conditions for interference, we said we have to have the same or at least non-orthogonal polarizations. We did the case when the sources were emitting nearly planar wavefronts, right? We assumed that the wavefronts are planar so that we could do the math more easily. We could write it as a harmonic plane wave, for example. And I say stable. I'll explain what I mean by stable in just a minute. And then we also said they must be quasi-monochromatic, meaning we assumed that all the waves had nearly the same frequency. Otherwise, and we'll see this again and again, that the phase difference between two waves, if the frequencies are different, then one is going at omega 1t, the other is going at omega 2t, and that difference will just quickly average to zero. Right? When one wave is at a maximum, the other will be at a minimum, because as time goes on, these waves are just getting out of phase with. Okay. So then that average between, will go between maximum, minimum very quickly, much faster than our eye can follow or the detectors can follow, and the time average will go to zero. And the last part, this is a very, very important condition for interference. And you'll come across this again and again. It has many experimental implications. So we should really understand this part, which is that the stable phase difference at time t equal to zero. What do I mean by this? This is that phase, we wrote down the interference condition, assuming, say, wave 1 has some extra phase epsilon 1, wave 2 has some extra phase epsilon 2. This is just the formula again. I'm reminding you. The interference condition is E01.E02 cosine delta. And the delta was given by this expression over here. Okay. K1.R1 minus K2.R2 plus epsilon 1 minus epsilon 2. Okay. So if this epsilon 1 minus epsilon 2, we already talked about, omega was assumed to be the same. If they are different, that will average to zero. In the same way, if this epsilon 1 minus epsilon 2 starts to fluctuate over time, if it's not stable, if it is in the same value, it can be non-zero. That's fine. But if it's not the same value from moment to moment, if it fluctuates very quickly and it's not stable, again, the same problem will arise because of this cosine function, right? If the epsilon 1 minus epsilon 2 is fluctuating over time, this will become sometimes a maximum, sometimes a minimum, and it will quickly average again to zero. Okay. So all of these considerations have to be satisfied for us to observe interference fringes with our eye or with most standard detectors, like cameras, photographic film, etc. Unless you work very hard, they're going to average over some time scale, which is say microseconds or milliseconds even, which is faster than our eyes, but still that's all much, much greater than the time scale in which these phase differences fluctuate. Then you're going to lose that interference condition, which is why we don't see interference very easily at times. Okay, it's not like we're always seeing interference. Interference conditions have to be carefully arranged, either in the lab or in nature by accident, whatever. Okay, so let's just talk about that in a little bit of a physical picture. So imagine that the wavefront E of t is some amplitude that's fluctuating, which is not super important. But then it has a central frequency, which we said it's quasi-monochromatic. What do I mean by that? It has a central frequency, 2 pi nu, I use nu instead of f. And then there's some phase, that epsilon, which we talked about as epsilon 1 or epsilon 2. Now we are assuming this epsilon is itself a function of time. Okay? And let's say that this epsilon varies slowly, but over some time duration, which we call delta tc. That is imagine that epsilon was say 0 initially, and then it jumps to some value, let's say pi over 2. And the time scale over which it jumps is this delta tc. Okay. Equivalently, I could say fix epsilon of t, but now let the frequency vary a little bit. Okay. Then it's the same idea because it's also there in the phase. If the frequency varied a little bit, and that's what is kind of shown here. I don't know if you can tell, but here's one wavefront, and then it maybe jumps and becomes another wavefront, and then sometimes it even spreads out a little bit in time. Okay, maybe hard to see here, but definitely the jumps hopefully can be seen on that graph. Okay, so the idea is that it goes in one phase relationship, and so this one and this one maybe have the same phase, and then over here maybe it jumps suddenly to go to a different phase. Okay, so this time duration over which the coherence time, with what we call the coherence time, this delta tc, is roughly how long it takes to fluctuate in frequency or in the phase. That's that phase difference. Okay, and it turns out, and I won't go into the detail right now, we'll come back to it later, which is that this delta tc is approximately proportional to the bandwidth of the source. So, we have, say, some light which has a central frequency, okay, like let's say a discharge lamp or a laser, and then it has some bandwidth. It's not exactly monochromatic, right? Which makes sense. Because a truly monochromatic wave, when you think about it, would be a wave that started at minus infinity in time as a sine wave and went to plus infinity in time as a sine wave and never changed its frequency forever, right? That's what a sine wave mathematically represents. But even if I took a laser and I turned it on in the morning and turned it off in the evening, well, that means that it's no longer perfectly monochromatic, right? Because it turned on and became a perfect sine wave, but that was at a finite time, and then I turned it off at some other finite time. It didn't go from minus infinity to plus infinity. By the very mathematical definition, that's no longer perfectly monochromatic. It's quasi-monochromatic. Of course, the bandwidth there will be very tiny. There are other considerations in a laser that make the bandwidth non-zero, even if I had the laser on forever from the start of the universe, okay? There are other things that go on in the physics of a laser which make the frequency fluctuate a little bit. Now you can look at other sources. Let's say your discharge lamp. Well, that's coming from a single atomic species, so it's actually pretty narrow. But then it's a bunch of atoms which are like hitting each other inside the discharge lamp. So the frequencies aren't exactly the same atomic transition all the time. Okay, there's some broadening due to thermal distribution, collisions, and so on. And then finally, of course, a normal white light source, LED source, or incandescent lamp, bulb source, etc. You can imagine they are very broadly spread out. There's a whole bunch of atoms which are very hot, and they're all emitting in like all different wavelengths and frequencies and so on. So it's going to be even more broad in its wavelength distribution. Okay. So all of that means that the coherence time, as we call it, the time over which this frequency or phase fluctuates, is typically for white light sources that we normally use, like the sun or LED lamp or whatever, is on the order of 10 femtoseconds, okay, or 10 to the minus 14 seconds. Very, very small, okay. So, okay, so from the coherence time, this delta Tc, which as I just told you is 1 over the sort of the bandwidth of the source, I can now define something called a longitudinal coherence line. Remember, for most of the interference experiments, we're interested in the phase, in the path length difference, R1 minus R2. We talked about that in the last class. So to compare that R1 minus R2 to a length instead of a time, right? This was a time. Delta Tc is a time, okay? So I want to convert that to a length. What do you think I could do to convert a length, a time to a length? Just, even if you don't know the answer, how do I go from the time to a length for a wave? Yes?
Use the velocity.
Use the velocity, exactly. So that's exactly what I do. I multiply the coherence time by the velocity c. That gives me a length. And this is the length over which that we have to compare any path length differences to. Okay. So this is now, I could imagine instead of looking at it in the time domain like I was doing in the previous slide, I looked at it in the spatial domain. So I froze the time and looked in the spatial domain. Then wavefronts will initially start out in phase at one position. By the time they get to a certain length, which is delta LC, they are now sort of randomly out of phase with each other. That same jump in the phase takes place now in the spatial domain, which is just c times the delta Tc, okay? And so that's the longitudinal length. We call it longitudinal because it's due to propagation. Like as we propagate in time, in space, along this propagation direction, they'll go out of phase. Or the phase relationship will no longer be stable. Okay, that's the most important thing. It's not stable anymore. Okay, it can be some constant value, as long as that constant value remains fixed for all time, for example. It starts jumping around and you can't predict it from time to time, then it becomes washing out of the interference fringes. So this is just to show you, if I now take this and divide by lambda on both sides, right? That delta LC is equal to C. Well, C over lambda is just nu bar, the central frequency, which is on the order of 10 to the 14 for visible light. Delta Tc, I told you, is on the order of 10 femtoseconds, which is the bandwidth of white light, is also 10 to the minus 14. This is on the order of 1. So what this is saying is, when delta LC is comparable to the wavelength, then things are stable. I can predict roughly the phase relationship, okay? When delta LC is on the order of a lambda, so we need also the phase difference in the interference experiments to be less than a lambda, on the order of a lambda or less. Well, I mean, we can be a little bit, so remember again, to observe the interference fringes, we need the path length difference now, R1 minus R2, to be less than this delta LC. And so since delta LC is on the order of wavelength, we'll typically put a condition that to observe interference fringes, we need the path length difference to be less than 5 lambda. Okay, not quite exactly lambda, because this was just a approximate, sort of relationship. As long as it's on the order of like 5 lambda or less, we will see a stable interference pattern. This is where that condition comes from in all your experiments. So you'll observe this in the Michelson. You may be wondering, what about the Newton rings and stuff? Well, there the interference, the path length difference is fixed again by the length of the thickness of the lens of the air film, etc. So all of that, in all these cases, basically we need this path length difference to always be less than a few wavelengths. Okay. For white, but as we make the source narrower, we can increase this condition or relax this condition. But always we can go back to what is the delta TC, the coherence time, which you can get from the bandwidth of the source. So the source is very narrow bandwidth, rather than being as spread out as white light. The narrower that bandwidth, the longer this delta TC is, and now we can extend out the path length difference. Maybe it can get up to hundreds of microns or millimeters, etc. I mean, you can even work this out, right? I mean, so basically delta LC over lambda is on the order of 1. Well, that means the path length difference can only be like a few hundred nanometers, right? That's the wavelength of light. Central wavelength of light is 500 nanometers for green, for white light. So you would have to say that I can't have a path length difference R1 minus R2 more than 500 nanometers, or a few times that, 5 times that. That's like, a micron, a couple microns. That's about all you can make the path length difference in a Michelson if you use pure white light. Now, if you use like a discharge source, it's not just a couple microns, it can be maybe 100 microns. A laser obviously can make it much longer. And I'll show you some examples of all that little bit. So, any questions about longitudinal coherence or temporal coherence? So it has multiple names. It's called temporal coherence. You understand that why? Because we just talked about that. Here, this is temporal coherence. And the spatial analogy or the spatial extent of that temporal coherence is called longitudinal coherence. Okay, so they mean the same thing. Even though this is a length and that's a time, they mean the same thing because one is related to the other. But now I'm going to introduce a new type of coherence. Okay, I'll explain that on the next slide, but any questions so far? Because this is a very important concept for interference. So now I introduce the concept of spatial coherence. So here I have a source, which is a point source. And this point source, imagine for a minute that it has perfect narrow bandwidth or infinitely small bandwidth. So it's perfectly monochromatic as well. Okay. So this is obviously a perfect source. It's both a point source and it is a perfectly monochromatic source. Then the waves that come out of this point source, you can see these are spherical waves. And eventually they'll look almost planar, but even on the spherical wavefront, you can see, say, let's look at point P1 prime. Well, it has a stable phase relationship. Knowing what I mean by that is if I know the phase at P1 prime, I know what the phase is at P2 prime. I just propagate out an extra distance and multiply by 2 pi over lambda. I'll know exactly what the phase is here, 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 here. It's all known along that line. So this is longitudinally, it's in perfect coherence, longitudinal, along the direction of travel. But because it's also emitting perfect spherical waves, this point source, it means that, say, point P1, which is on the wavefront, and this is true for planar wavefront and for spherical wavefront or cylindrical wavefronts, the point P1, P2, and P3 are all in perfect, stable phase relationship. I know exactly what the phase is at the points P1, P2, P3. Well, in this case, they are identical. Okay, they have the same phase. But also I know the relationship between, say, P1 and P3 prime. Because I know that P3 prime and P2, I know that phase relationship to a stable amount. So therefore, I know this relationship to P1 and P3 prime as well. So this source, we say, has perfect temporal coherence, which, as I've just told you, is the same as longitudinal coherence. But it also has what we call spatial or transverse coherence, meaning along the wavefront. The wavefront is well defined, and we know exactly where on the wavefront that we can look at the wave. Okay. Now let me show you a source which doesn't have perfect temporal coherence. So now imagine that the source is still a point source, but no longer has perfect temporal coherence. So it has fluctuating frequency, like we just discussed. So now you can see there's a group of waves within this longitudinal coherence length. I can predict what the phase relationship is going to be. Again, just by the same argument that we had before, that within this group of waves, knowing the wavefront, the phase here, I can predict what it is here. But then it might jump. I might get a slightly different wavelength or slightly different frequency, right? That's what is basically going on. When the frequency jumps, it's like saying the wavelength has jumped. So now you see the waves are spread out further because it's a different wavelength now. Okay. Now again, I can predict between P1 prime, P2 prime, and P3 prime. I can predict the relationship. Okay, and I can also predict the relationship between P1, P2, and P3, but I've lost any predictability with this group of waves. This group of waves no longer has the same relationship as this one, so I can't quite predict anymore what that wavefront is going to look like. So this guy has perfect spatial coherence, but imperfect temporal or longitudinal coherence. Is that clear? What I mean by spatial coherence? Now imagine I have more than just one point source. I have multiple point sources. I'm not going to show you that case, but you can imagine things can get rapidly very unstable if I have multiple point sources, all of which might have varying fluctuating frequencies and so on. Now you can see this spatial coherence can also get messed up. Okay, and so that is basically what's happening in most sources. Most sources are not point sources. They have some extent to them in the transverse direction, if you like. And so that makes these wavefronts get messed up as well, and they no longer relate to each other along this wavefront here. Here, P1, P2, P3, I can still know exactly what that relationship is. But once I start introducing other wavefronts in there, now the phase at P1 is a sum of all the waves from all the other sources at P1. And these guys are all fluctuating with respect to each other. So now P1 itself has a very random wavefront at it. And similarly, P2 and P3, that phase relationship between them is going to get messed up very quickly. Okay? That's the basic intuition for it. And so one of the problems was that without the spatial coherence, we can't get good interference as well. Okay? In fact, in 1801, Thomas Young, after who we named this interference, the Young's double slit, he solved the problem of creating spatially coherent sources without a laser. Because about 150 years before him, Grimaldi tried to do the Young's double slit experiment, or the double slit experiment. What he took the sunlight, right? That's the only real source of bright light that they had back then, and he just focused it onto two pinholes, okay? And he didn't get anything. And the reason is sunlight is still an extended source even for us here on Earth. Even though the sun is only like a little disk in the sky, it's still too extended of a source when we view it on the Earth. He would have been better off using starlight, but of course, starlight is extremely faint, and because stars look almost like a point source here on Earth. But of course, starlight is extremely faint, and he would have never been able to see the interference pattern from star. Okay, so that is the problem that Grimaldi had, and he didn't know it, right? He didn't understand all this physics. So it took Thomas Young to intuit this physics. That this is a new kind of understanding that he built by understanding that if I take this messed up wavefronts from a lot of extended sources, like the sun or a lamp or whatever, and put it on a pinhole, one pinhole. Now, even though I have lost the temporal coherence, I can't do anything. That's still dependent on the wavelength spread or the frequency spread of the source. But the spatial coherence I can fix, just like I showed you on the previous. Now the wavefronts coming out of this pinhole are very nicely spatially coherent on the transverse direction. And so was born the first wavefront splitting interferometer, or the Young's double slit interferometer. So what he did was to take a first pinhole, create a spatially coherent wavefront, put it on this other screen with like two pinholes, and in a darkened room, he was immediately able to observe the interference rings. This is a brilliant experiment for that time because it took so much cleverness to understand this and to implement it in a careful way. And so that's how he got the Young's double slit experiment to work. In modern version of this is instead of using pinholes, we use slits. That is the only main difference is a slit allows a lot of light through compared to a pinhole, right? And because everything else remains essentially the same, like if I were to look like at a cross section, it looks just like pinholes. Of course, now I have symmetry in and out of the board, so there's like, a cylindrical wave that's coming out rather than spherical waves. But that's the only main sort of difference. Everything else in terms of the understanding of the physics of this is remaining the same. Okay, so let's go through the math of the Young's double slit now that we understand the intuition for it. So the math is very straightforward. We need to calculate the path length difference between the wave going from S1 to S2. Okay, so S2 to P and S1 to P, we need that path length difference. When we have that path length difference, if it's equal to an integer multiple of lambda, that will be a constructive interference. And if it's an odd multiple of lambda over 2, it'll be a destructive interference. So to calculate the path length difference, let's again, we're under the assumption that this slit separation A, remember for all the conditions of interference, like we usually assume, the slit separation A is much smaller than the distance to where we are observing things. And also it's all of this is much greater, this distance S is much greater than a wavelength. Okay, so it's greater than A and it's greater than a wavelength. This S, the distance to the source, from the sources to the screen. Okay. What else? Okay, so now at this point it's just geometry. We need this distance, this difference. You can see here that the difference between the two waves, the optical path length, is basically just this little part, this little piece over here that's extra when we look at an angle theta. So that's kind of zoomed in over here. So this little section S1B is equal, I'm claiming, to S1P minus S2P. Okay, which you can see from the drawing is approximately true. You can make it more exact if you want by calculating the cosine law and making the approximation. But for now, if we just say that S1B is the path length difference, then we just need to calculate it. Then if this angle is the angle at which we are observing the point, the fringe, the interference pattern, this is the angle of observation from the central axis, which is the halfway distant between S1 and S2. Okay. And if this theta is the angle here, that same angle is this angle over here. Okay, because that's just the normals to all of those rays, so we can immediately calculate that this is also angle theta. And so in this triangle, theta is this angle, so sine theta is just this distance S1B divided by A, the hypotenuse, and therefore the R1 minus R2 then, which is S1B, is equal to A sine theta. A being the separation between the slits S1 and S2. Okay, and for small angles theta, which will be true in the far field, remember far field, we're just taking the screen out very far away, so the pattern of the interference fringes never changes once you get into the far field, but just the distance between the fringes will change. And that is also clearly seen here, is just A times the angle theta. So as I get further and further out, the path length difference just grows, but it remains of the same type, which is A, which is fixed by A, the number, the slit distance. And that, of course, this theta, which is sine theta is equal to theta, is also equal to tan theta. And tan theta in this triangle, this big triangle over here, you look at this big triangle, okay? So right here, sorry. So this is the central region up to the point O, up to the point P. That big triangle over there, tan theta equals Y divided by S. Okay, so substituting that, I get A times Y divided by S. And that all gives me A sine theta equals M lambda. Again, this is obtained by just setting the path length difference times K. K is 2 pi over lambda, has to be equal to 2m pi. Or even multiple of 2 pi. Okay, or even multiple of pi. And from that, I get then this condition, Ym. You don't need to remember all the formulas as long as you can remember that the path length difference is A sine theta. Once you have the path length difference, then just use the standard result that that's k times the path length difference is equal to 2m pi for constructive interference. And the spacing between the fringes, well, clearly for m equal to something, it's s over a times m lambda, y m plus 1, that would be the next order. We call this m as the order of the fringe. So in between one fringe and the other, the path length difference is going to be how much? So from one fringe to the next fringe, what's the path length difference? I go from m lambda to the next fringe. Next to it will be m. One and a half. That would be the minimum.
Oh, so that's it.
Yeah. So it'll be either m plus 1 or m minus 1. Right. So if I have the mth fringe, then the next brightest fringe to this side will be m minus 1. The brightest fringe to the other side will be m plus 1. So starting with the one maxima, going to the next maxima changes the path length by 1 lambda. Okay. So the spacing between the fringes, then I can just write down immediately as just the difference between s over a m lambda and s over a m plus 1 or m minus 1 lambda. So the spacing between this fringe and the next one in the screen is just s over a times lambda. Okay. And this gives me an important sort of general result. It turns out, although I derived this for the Young's double slit, you'll notice the spacing between fringes is proportional to 1 over the distance between the slits. Okay. So smaller the wavelength, the larger, smaller the spacing between the slits S1 and S2, larger is the separation of the fringes in that screen. Similarly, for larger the separation between the slits, smaller is the fringe spacing. Okay. So this is why we need to get to small separations to see the fringes more clearly, because it makes the fringe spacing larger and larger. And this is a very general result. Even though I only derived it for the Young's double slit, you'll see nearly all the interference patterns, diffraction patterns, all these patterns will have this behavior that the spacing between the maxima or minima will go as 1 over some feature of the source, some aspect of the source that governs its dimensions. So spacing between the fringe is a reciprocal of the spacing in the source, basically. Okay. This is a Fourier relationship that is well known. Okay. And in fact, there's a deep connection, of course, to Fourier analysis and all this stuff. But I just want to point it out here. Also, you'll see it's directly proportional to the wavelength, obviously. So if I look at this fringe pattern, if I had a blue light, which is like blue light has higher frequency, so lower wavelength, right? And the red light has larger wavelength, lower frequency. So then I would get a color space. If I send in truly white light with blue and red, in any one fringe, I would see blue, then green, then red, going out further and further, right? Starting from, say, the central fringe, and I walk off to the side. The first fringe I'll see will be the blue, then the green, then the red, and so on, or orange, whatever, just the spacing of the colors in the rainbow. But they'll be sort of opposite to what you saw in the rainbow problem in the class, because there we see red down to blue, here we see blue up to red, starting with in the angles. Okay. All right. And the radius distribution, well, that's just a formula. I mean, I don't typically think you'll need it, but it's there. That's the intensity distribution. Okay, so that okay, this is the effects of finite coherence. I've already talked about it quite a bit, but I'm just sort of showing it to you as a picture now. So you have like a wave group from the first source, S1, wave group from the second source, S2. And if the path length difference, R1 minus R2, is greater than the longitudinal coherence length, then initially you see A1 and A2, this is the same wave packet, right? They have the same phase relationship. B1 and B2 have the same, C1 and C2 have the same, D1 and D2 have the same. But you can see when R1 minus R2 is greater than this coherence length, the longitudinal coherence length, now we start to see interference between, say, H2 to I1, which is two separate wave packets. And now these two have no stable phase relationship between them, and the interference fringe gets washed out. Okay? So this is what I was talking about. So, and then if you if you now have R1 minus R2 lesser than delta LC, the coherence length, then the same wave packet H1 and H2 overlap with each other at the point P, and you get a stable interference pattern. Okay. So for other experimental considerations, just quickly I'll go over this. So we want, for a laser source, we want the laser beam to be like almost like a plane wave and illuminating both the slits equal. Okay, that's when you'll get the nice interference pattern. So if the laser beam is very small compared to the size of the separation of the slits, you may have to expand the laser beam. So that's just one experimental consideration. Here I just use a Galilean expander to keep things compact and expanded it and put it on the aperture, on the screen. Of course, the other situation you might have is a discharge lamp, which is not very monochromatic, not an atomic line source, which is what you were using. I think you were using a sodium lamp in your, which is still, it's a discharge lamp. And so you might have noticed there's a filter in front of it, okay, just to cut out other wavelengths of light. And then what you'll see, I mean, okay, so then again, you use it to like create, you focus it with a lens onto this source over here, okay? And then, sorry, a pinhole over here. And then the pinhole, you know, again, we you use a lens to make the waves all nice and planar from this source, and then hit the aperture, which has the two slits in it. And then sometimes what you'll see, instead of like simply moving the screen very far away, which might make the system very non-compact, you put a lens in it. And what does the lens do? Well, if the lens is exactly a focal length away from the aperture, then the image of the aperture will be at infinity, basically. And so what will be, we can put the screen anywhere we want, basically, right? Or, you know, at a distance f even, it doesn't matter. We'll see that, you know, plane waves get focused here, creating the interference pattern. But effectively, we have put the image of this or the viewing area, we put it effectively at infinity, even though it's at a finite distance from the screen. This is a common thing you'll see even in your diffraction experiments and so on, where you put a lens right after the diffracting screen, because that effectively moves the viewing area into the far field. That's called a far field interference pattern. Okay. All right, before we finish, I just thought I would make sure everybody is following this. So let's just quickly think about this for a minute, and then I'd like to hear your answers before we finish for the day. So suppose in Young's double slit experiment, I kept everything else the same, the slit size and the distance to the screen and everything, but I just switched the wavelength from green to red. If I were to compare the spacing between the fringe maxima in the first case to the spacing between fringe maxima in the second case, from green to red, will it increase, decrease, stay the same, or I haven't given you enough information? Want to talk to your neighbors? Sorry. Spacing between fringe maxima. This is also an example of the type of questions you're going to see on exams. So you should be able to reason about this without even doing the math. I'll have each group give me an answer just to see where the groups are at. You don't have a group, is it okay? You have an answer? Okay, hold on.
Yeah. So if we increase
Yeah, not enough people here, but it's okay. You guys all get the secret quiz question. Okay, let's go around and take a poll. So your group here, what do you think?
decrease.
Decrease, okay. Increase, okay. Group over there, Nigel and Jack. Decrease. Increase, okay. Group over there. Increase, okay. And the back group. What do you folks think? Increase. Decrease. Okay, we seem to be roughly split between increase and decrease. Interesting. Okay. So remember that the spacing between the fringe maxima is proportional to what? It's 1 over the slit size, but directly proportional to wavelength. So is green lower wavelength or higher wavelength than red? Lower wavelength. So when I go from green to red, the spacing will increase. You just said everything right except the answer.
Maybe I'm
So the spacing between the maxima is proportional to the wavelength.
Yeah.
So if I go from green to red, red is longer.
From red to green.
Oh, green.
Yeah, I
red.
know. I had to fix one.
Okay.
I like the whole time. I was like, yeah, red.
Okay, so you had the reasoning right, you just didn't read the question. Okay, fine.
I was like infrared. Let me get
Infrared.
infrared.
All right, very good.